This is not merely a dead star drifting through the void. This is something far stranger, something that challenges everything we thought we understood about how stars die and what comes after. Scientists call it SGR 0501 plus 4 516, but perhaps a more fitting name would be a zombie star, a remnant that refuses to rest quietly, that instead hurls itself through the galaxy at velocities that suggest an origin more violent than we can easily imagine. Where did it come from? What catastrophic event could have launched it on this extraordinary journey? And what does this single wandering object tell us about the hidden mechanisms of stellar death that play out across the universe? To understand why this zombie star presents such a profound mystery, we must first understand what it actually is. SGR 0501 plus 4 516 belongs to an exotic class of objects known as magnetars, which themselves represent a subset of neutron stars, which in turn represent one possible endpoint for certain types of massive stars. The story begins with stellar evolution itself, the life cycle that all stars follow from birth to death. When a star is born from collapsing clouds of gas and dust, its ultimate fate is already written in the amount of mass it contains. Stars like our Sun will eventually swell into red giants, shed their outer layers, and leave behind dense cores called white dwarfs. But for stars born with much greater mass, perhaps 10 times the mass of the Sun or more, the ending is far more dramatic and violent. These massive stars burn through their nuclear fuel at prodigious rates, fusing hydrogen into helium, then helium into carbon, oxygen, and heavier elements in a cascading series of fusion reactions. Each stage burns faster and hotter than the last until the core is producing iron. Iron represents a dead end in this fusion chain because fusing iron consumes energy rather than releasing it. When the core fills with iron, suddenly there is nothing left to support the star against its own crushing gravity. In a fraction of a second, the core collapses catastrophically. Matter falls inward at nearly a quarter the speed of light, compressing to nuclear densities. Then, as the collapse halts and rebounds, a shockwave races outward through the star's outer layers, tearing it apart in what we observe as a supernova explosion, one of the most energetic events in the universe. What remains at the center, if the original star was massive enough, is a neutron star. These objects are almost incomprehensibly dense, packing roughly 1.5 times the mass of our entire Sun into a sphere perhaps 20 kilometers across, about the size of a city. A teaspoon of neutron star material would weigh about 1 billion tons on Earth. The matter inside is compressed so tightly that protons and electrons are crushed together to form neutrons, hence the name. The entire object becomes essentially a single giant atomic nucleus, held together by gravity and the quantum pressure of neutrons packed as tightly as the laws of physics permit. But not all neutron stars are created equal. Most spin rapidly, perhaps several times per second, and emit beams of radio waves from their magnetic poles, creating the lighthouse effect we observe as pulsars. These objects have powerful magnetic fields, thousands or millions of times, stronger than anything we can create on Earth. Yet even among these extreme objects, magnetars stand apart. A magnetar takes the concept of a neutron star and amplifies the magnetic field by factors of hundreds or thousands. While a typical neutron star might have a magnetic field strength of 1 trillion times Earth's magnetic field, a magnetar can reach 100 trillion times stronger, or even 1,000 trillion in extreme cases. The magnetic field of SGR 0501 plus 4 516 exists in a realm that fundamentally challenges human intuition. To say it is roughly 100 trillion times stronger than Earth's protective magnetic bubble is to state a number that our minds cannot truly grasp. We experience magnetism in our daily lives through refrigerator magnets, compass needles, and the gentle force that shields our planet from harmful solar radiation. Earth's magnetic field extends thousands of miles into space, creating the magnetosphere that deflects charged particles from the sun and prevents our atmosphere from being stripped away. This field measures roughly half a Gauss at Earth's surface, a comfortable and life-sustaining strength. The zombie star's magnetic field reaches approximately 10 to the 15th Gauss, or 1 quadrillion Gauss, a number so large it becomes almost abstract. But what actually is a magnetic field? At its most fundamental level, a magnetic field is a region of space where magnetic forces can be detected, forces that arise from moving electric charges. In planets like Earth, the magnetic field is generated by electric currents in the molten iron core. In neutron stars and magnetars, the mechanism is related to the extreme conditions during their formation. When the core of a massive star collapses, any magnetic field that existed in the original star is compressed along with everything else. Just as a figure skater spins faster when pulling in their arms, conserving angular momentum, a magnetic field becomes vastly stronger when compressed into a tiny volume. Additionally, in the first few seconds after the neutron star forms, intense convection currents in the superhot matter can amplify the magnetic field through a dynamo mechanism. For reasons scientists are still working to understand fully, some neutron stars emerge from their violent births with magnetic fields that are orders of magnitude stronger than their siblings, becoming magnetars. The strength of this magnetic field is not merely an interesting number for astrophysicists to measure and catalogue. This field has real, tangible, and terrifying effects on the space around it. Consider a thought experiment that scientists have used to illustrate the power of a magnetar's magnetic field. If you were to place a credit card or any other object with a magnetic strip at roughly half the distance between Earth and the Moon, about 120,000 miles from SGR 0501 plus 4, 516, the magnetic field would be strong enough to completely erase the magnetic information on that strip. The card would be wiped clean by a magnetar that was still farther away than most satellites orbit Earth. This gives us some sense of the field's reach and intensity, but it barely scratches the surface of what this object is capable of. Move closer, and the effects become not merely inconvenient, but fundamentally destructive to matter itself. At a distance of roughly 600 miles, approximately the distance from New York City to Detroit, the magnetic forces would become lethal in a way that transcends ordinary concepts of death or injury. Human tissue, like all matter, is held together by electromagnetic forces, the electrons orbiting atomic nuclei, the chemical bonds between atoms, the very structure of molecules that make up our cells and organs. All of these depend on electromagnetic interactions. When exposed to a magnetic field of sufficient strength, these interactions are simply overwhelmed. The magnetic forces become stronger than the electromagnetic forces holding matter together. At 600 miles from the zombie star, your body would not burn or freeze or be crushed. Instead, it would begin to disintegrate at the atomic level. The atoms themselves would be distorted, their electron clouds stretched and deformed by magnetic forces stronger than the electrical attraction between electrons and nuclei. Chemical bonds would break as molecules were literally pulled apart by magnetic stress. The distinction between different types of matter would begin to break down. You would not experience this process because the signals in your nervous system, which depend on electrical impulses and chemical neurotransmitters, would cease to function instantly. you would simply cease to exist as an organized structure, your constituent atoms scattered and transformed by forces more powerful than anything else in nature, except perhaps the interior of a black hole. This is the destructive capability sleeping within the zombie star, a weapon so powerful it doesn't need to touch its target or even come particularly close. The discovery of SGR 0501 plus 4 516 came in the way many astronomical discoveries come, suddenly and unexpectedly. In August 2008, astronomers detected something unusual approximately 15,000 light-years from Earth. This distance, while vast by human standards, is relatively close on galactic scales. Our Milky Way galaxy stretches roughly 100,000 light-years from edge to edge, so this object was located in our general galactic neighborhood. What caught the astronomers' attention was not the object itself, which had been too faint and dim to notice previously, but rather a dramatic announcement of its presence. The zombie star suddenly began emitting intense bursts of high-energy radiation, particularly X-rays and gamma rays. These bursts were detected by satellites monitoring the sky for transient high-energy events, part of a global network designed to catch fleeting cosmic phenomena. This behavior is characteristic of magnetars, which are known for sudden outbursts of radiation thought to be caused by starquakes, sudden fractures in the neutron star's crust caused by stresses in the intense magnetic field. As the crust cracks and shifts, it releases enormous amounts of energy, much as earthquakes on Earth release energy built up in tectonic plates, but on a scale billions of times more powerful. These outbursts allowed astronomers to pinpoint the zombie star's location and begin studying it in detail using various telescopes and instruments. What makes this discovery particularly significant is the extreme rarity of magnetars. In our entire Milky Way galaxy, which contains somewhere between 200 and 400 billion stars, astronomers have confirmed the existence of only about 30 magnetars. This number is remarkably small, considering the vast stellar population. Even among neutron stars, which themselves are relatively uncommon, magnetars represent a tiny fraction. Astronomers estimate there might be around 100 million neutron stars in our galaxy, the remnants of all the massive stars that have exploded over billions of years. Of these, only about 3,000 have been detected as pulsars, the rotating neutron stars whose beams sweep across Earth like cosmic lighthouses. And of those thousands of pulsars, only about 30 are magnetars. This rarity suggests that the conditions required to create a magnetar must be quite specific and unusual. Not every massive star that explodes in a supernova will leave behind a magnetar. Perhaps it requires a particular mass range, or a specific rotation rate, or unusual properties in the original star's magnetic field. Perhaps the conditions during the core collapse and rebound must be just right to generate and sustain such an intense magnetic field. Scientists have proposed various theories, but the truth is that we don't fully understand why some neutron stars become magnetars, while the vast majority do not. Each magnetar discovered, therefore, is precious, a rare specimen that might help us decode the recipe for creating these extreme objects. After the initial detection in 2008, astronomers continued to monitor SGR 0501 plus 4 516 using various instruments. Among the most valuable observations were those made by the Hubble Space Telescope, humanity's most famous orbital observatory, which has revolutionized our understanding of the universe since its launch in 1990. Hubble's sharp vision, unblurred by Earth's atmosphere, can measure the precise positions of stars and other objects with extraordinary accuracy. The European Space Agency's Gaia spacecraft, launched specifically to create a three-dimensional map of our galaxy, provided additional crucial data. Gaia has been measuring the positions, distances, and motions of more than 1 billion stars, creating the most detailed galactic census ever attempted. By comparing observations taken years apart, astronomers can detect tiny shifts in an object's position against the background of more distant stars. This proper motion, as it's called, reveals how fast and in what direction an object is moving across our line of sight. Combined with measurements of radial velocity, the motion toward or away from us, measured through the Doppler shift of light, astronomers can reconstruct an object's full three-dimensional motion through space. This technique has been used to track the movements of countless stars, revealing the complex dance of stellar motions within our galaxy. But when astronomers applied this technique to the zombie star, they discovered something unexpected and puzzling. The measurements revealed that SGR 0501 plus 4516 was not drifting sedately through space like most stars in the galactic disk. Instead, it was racing along at an extraordinary velocity of more than 110,000 miles per hour, or about 50 kilometers per second. To put this in context, our Sun orbits the galactic center at roughly 500,000 miles per hour, but this motion is shared by most stars in our region of the galaxy, all of us following roughly circular orbits around the massive black hole at the galaxy's heart. What matters is not absolute velocity, but velocity relative to the local standard of rest, the average motion of stars in the neighborhood. By this measure, most stars move at relatively modest speeds, perhaps tens of thousands of miles per hour at most. The zombie star's speed exceeded this by a significant margin. This high velocity immediately told astronomers something important about its history. Objects don't simply start moving at such speed spontaneously. Something must have accelerated it, must have imparted a tremendous amount of energy to launch it on this trajectory. The most obvious explanation was the same supernova explosion that created the neutron star in the first place. Supernova explosions are rarely perfectly symmetric. If the explosion is even slightly lopsided, with more matter and energy ejected in one direction than another, the newly formed neutron star will recoil in the opposite direction, like a rifle kicking back when it fires a bullet. These natal kicks, as astronomers call them, can impart significant velocities to neutron stars, sending them flying away from their birthplaces at speeds of hundreds of kilometers per second in extreme cases. So the zombie star's high velocity was unusual but not unprecedented. What made it truly mysterious was where it appeared to be coming from. When astronomers traced its trajectory backward through time, rewinding its motion to see where it had been thousands of years ago, they made a puzzling discovery. Not far from the zombie star's current position, there is a structure called HB9, the remnant of an ancient supernova explosion. HB9 is an expanding shell of gas, the debris from a massive star that exploded roughly 10,000 years ago. When astronomers first realized the zombie star was racing through space, HB9 seemed like the obvious candidate for its birthplace. The proximity was suggestive. Perhaps this magnetar was born in the explosion that created HB9, kicked out of the remnant by an asymmetric supernova, and had been traveling ever since. It would have been a satisfying explanation, tying together two objects in the same region of space with a common origin story. Astronomers began working under this assumption, treating HB9 as the zombie star's home. But as they refined their measurements and traced the magnetar's path more carefully, cracks began to appear in this neat explanation. The problem was direction and timing. When you run the zombie star's motion backward, following its trajectory into the past, the path simply doesn't intersect with HB9. The zombie star appears to be moving in the wrong direction, heading away at an angle that doesn't align with a birth in that supernova remnant. Moreover, even if the direction had been right, the timing was problematic. Based on its current distance from HB9 and its velocity, if it had been travelling in a straight line from that remnant, it would have left much longer than 10,000 years ago, before the supernova that created HB9 even occurred. This realization forced astronomers to abandon the HB9 connection and begin searching elsewhere. Perhaps there was another supernova remnant along the zombie star's backward trajectory, one that had faded or been missed in previous surveys. Perhaps there was a massive star cluster that could have been its birthplace. The researchers carefully examined the region of space the magnetar had traversed over the past several thousand years, looking for any structure that could explain its origin. They searched for young star clusters, places where massive stars are born and die in relative proximity. They looked for other supernova remnants, faint shells of gas that might have escaped detection. They examined regions of active star formation where massive stars might have recently exploded. What they found was nothing. No suitable candidates existed anywhere along the zombie star's path into the past. No supernova remnants aligned with its trajectory. No young star clusters sat in the right position. It was as if the magnetar had simply appeared in space, already travelling at high velocity, with no obvious birthplace. This negative result was, in many ways, more puzzling than any positive detection would have been. In science, we expect to find causes for effects, origins for objects, explanations for observations. The universe follows rules, and with enough data and careful analysis, those rules usually reveal themselves. But in this case, the zombie star seemed to defy explanation, a stellar corpse with no apparent grave. This mystery led astronomers to consider more exotic possibilities. If traditional supernova explosions couldn't explain the zombie star's origin and trajectory, perhaps something more unusual had created it. One intriguing possibility involves white dwarfs, a completely different type of stellar remnant than the massive stars that typically produce neutron stars. White dwarfs form when stars like our Sun, too small to explode as supernovae, shed their outer layers and leave behind their hot, dense cores. These cores, roughly the size of Earth but containing the mass of the Sun, slowly cool and fade over billions of years. White dwarfs are common in our galaxy, the final resting state for most stars. They seem utterly unlike magnetars, objects separated by vast differences in mass, density, and origin. But what if a white dwarf didn't end its existence peacefully fading into darkness? Under certain circumstances, a white dwarf might gain additional mass. If it exists in a binary system with a companion star, matter could flow from that companion onto the white dwarf's surface, gradually increasing its mass. As the white dwarf accumulates more and more matter, it approaches a critical limit called the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. This limit represents the maximum mass that electron degeneracy pressure, the quantum mechanical effect that holds white dwarfs up against gravity, can support. When a white dwarf exceeds this limit, electron degeneracy pressure is no longer sufficient to prevent gravitational collapse. Normally, when a white dwarf approaches the Chandrasekhar limit, carbon fusion ignites explosively in the ultra-dense, ultra-hot conditions, and the entire white dwarf is torn apart in what we observe as a Type Ia supernova, an explosion bright enough to be seen across billions of light years and used as standard candles to measure cosmic distances. But theory suggests another possibility. Under certain conditions, if the composition is right and the accretion occurs in just the right way, a white dwarf might instead collapse directly into a neutron star without exploding. The outer layers would fall inward, compressing past white dwarf densities into the realm of nuclear density, creating a neutron star. This white dwarf collapse scenario would look very different from a traditional core collapse supernova. There would be little or no explosive ejection of matter, no bright supernova remnant expanding into space. The transformation would be relatively quiet, at least by cosmic standards, producing a neutron star without the dramatic fireworks we usually associate with their formation. If this is how the zombie star formed, it would explain why no supernova. Remnant can be found along its trajectory. There simply was no energetic supernova explosion to leave a remnant behind. The original star transitioned into a neutron star through a different mechanism entirely. The white dwarf collapse hypothesis also potentially explains how such an event could produce a magnetar specifically. The conditions during the collapse would still be extreme, still involving the compression and amplification of magnetic fields as matter is squeezed to nuclear densities. The dynamo mechanisms that might amplify magnetic fields in traditional core collapse supernovae could still operate during a white dwarf collapse. In fact, some theoretical models suggest that the particular physics of white dwarf collapse might even favor the creation of stronger magnetic fields, though this remains speculative. If correct, this mechanism might be an underappreciated route to magnetar formation, operating quietly in the galaxy while we've focused our attention on the spectacular deaths of massive stars. The implications of this alternative formation channel extend far beyond explaining a single mysterious object. For decades, astronomers have built models of stellar evolution, tracking how stars of different masses evolve, die, and contribute various elements to the galactic ecosystem. These models predict how many neutron stars should form per century in a galaxy like ours, based on the rate of massive star formation and the fraction that have enough mass to explode as supernova. If white dwarf collapse can also produce neutron stars and magnetars, these predictions need to be revised. There may be additional channels for creating these extreme objects that our models haven't fully incorporated. This has particularly important implications for understanding the birth rate and total population of magnetars. If magnetars can form through white dwarf collapse in addition to traditional supernovae, then we might expect more of them than our current models predict. Alternatively, if the white dwarf channel preferentially produces magnetars rather than regular neutron stars, it might help explain why magnetars are so rare compared to the total neutron star population. Each formation mechanism might produce neutron stars with different properties, different magnetic field strengths, different masses, different spins. Understanding the full variety of paths to neutron star formation helps us understand the diversity we observe in the neutron star population. Moreover, this discovery connects to one of the most exciting and mysterious phenomena in modern astronomy, the enigma of fast radio bursts. These are brief, intense flashes of radio waves that last only milliseconds, but release as much energy as the sun emits in days. First detected in 2007, fast radio bursts have challenged astronomers' understanding of what physical mechanisms could produce such intense, brief signals. Early observations suggested these bursts were coming from extremely distant galaxies, billions of light years away, which meant they had to be extraordinarily powerful to be detectable across such vast cosmic distances. One of the puzzles about fast radio bursts is that some appear to originate from galaxies that are relatively old, containing predominantly older stars. This presents a problem for theories that attribute these bursts to young neutron stars formed in recent supernova explosions. Old galaxies have low rates of massive star formation and supernovae. If fast radio bursts require recently formed neutron stars, we wouldn't expect to see them coming from ancient galaxies where the last supernovae occurred millions or even billions of years ago. Yet we do observe such bursts from old stellar populations, suggesting that whatever produces them can form or persist in environments that lack young, massive stars. Magnetars have emerged as leading candidates for producing at least some fast radio bursts. The intense magnetic fields and rapid rotation of magnetars could generate powerful outbursts of coherent radio emission through various proposed mechanisms. Some fast radio bursts repeat, and astronomers have successfully associated a few repeating sources with specific magnetars in our galaxy and nearby galaxies, providing strong evidence for this connection. However, if magnetars can only form in supernovae of massive stars, this doesn't easily explain fast radio bursts from old galaxies. The white dwarf collapse mechanism offers a potential solution to this puzzle. White dwarfs exist in enormous numbers in all galaxies, young and old. Binary systems where white dwarfs might accrete matter from companions are common throughout the universe. If white dwarf collapse can create magnetars, then these objects could form even in old elliptical galaxies where massive star formation ceased billions of years ago. This would provide a mechanism for generating magnetars, and potentially fast radio bursts, in stellar populations of any age. A fast radio burst detected coming from an ancient galaxy billions of light years away might originate from a magnetar that formed not in a recent supernova, but in the collapse of a white dwarf in a quiet binary system. This elegant solution could help explain the full diversity of fast radio burst sources we observe across the cosmos. Given its tremendous velocity, one might naturally wonder where the zombie star is heading. Is it on a collision course with anything? Will it eventually threaten our solar system or other inhabited worlds, presuming any exist? The answer, fortunately, is that we are in no danger whatsoever. Space is unimaginably vast, and even objects traveling at extreme speeds have essentially zero probability of colliding with anything specific. The zombie star is racing through the galactic disk, but that disk is mostly empty space punctuated by widely separated stars. At its current velocity of roughly 50 kilometers per second, it would take thousands of years for the magnetar to cross even a small fraction of the galaxy. Astronomers can project its trajectory forward, tracing where it will be in the future as it has been traced backward into the past. Based on its current path, it will continue through various regions of the Milky Way, passing within light years of countless stars, but likely never approaching within the actual distance where its intense magnetic field or other properties could affect them. The question of whether it might eventually escape the galaxy entirely depends on its precise velocity and the galaxy's gravitational potential. Escape velocity from the Milky Way at our distance from the galactic center is roughly 500 kilometers per second. The zombie star's velocity, while high by the standards of typical stellar motions, is well below this threshold. Gravity will keep it bound to our galaxy, though its orbit will be highly eccentric, taking it through different galactic environments as it circles the center over hundreds of millions of years. The zombie star's journey through the galaxy will continue for billions of years, slowly fading as its internal heat left over from its violent formation gradually radiates away into space. Unlike ordinary stars that generate energy through nuclear fusion, neutron stars have no ongoing power source. They glow primarily from residual heat, slowly cooling from the millions of degrees at their surface down toward the cold of interstellar space. This cooling process is extraordinarily slow. Even after billions of years, neutron stars remain warm enough to emit faint radiation detectable by sensitive instruments. As it cools, the magnetar's violent outbursts of high-energy radiation will gradually diminish and eventually cease. It will transition from an active, bursting magnetar to a quiet neutron star, and eventually to a cold, dark object no longer easily detectable except through its gravitational influence. To definitively determine whether the zombie star formed through white dwarf collapse or through some other unusual mechanism, astronomers need additional data. The key evidence would be finding or ruling out possible progenitor systems along its trajectory. If researchers could identify a binary system in the right location that had recently lost a white dwarf, this would strongly support the white dwarf collapse hypothesis. Alternatively, discovering a faint or unusual supernova remnant that had been missed in previous surveys could resurrect the traditional formation scenario. Improved measurements of the magnetar's distance, velocity, and trajectory would help narrow down its possible origin point, providing a smaller region of space to search in detail. Future observatories will play a crucial role in this investigation. The James Webb Space Telescope, with its unprecedented infrared sensitivity, might detect faint structures or stellar populations in the region the zombie star traversed. The upcoming Vera C. Rubin Observatory, which will survey the entire visible sky repeatedly, might discover new transient phenomena or faint nebulae relevant to the magnetar's origin. Advanced X-ray observatories could provide more detailed observations of the magnetar itself, revealing properties that might indicate its formation mechanism. As our instruments become more sophisticated and our surveys of the sky become more complete, the chances improve of finding the smoking gun evidence that will finally reveal where this object came from. The broader search for other rogue magnetars with mysterious origins has also intensified. If the white dwarf collapse mechanism is real and operates commonly enough, there should be other magnetars in similar situations, racing through the galaxy with no obvious supernova remnants in their past. Finding additional examples would transform this from a single puzzling case into a recognized phenomenon, a class of objects with a common origin story. Astronomers are now surveying known magnetars more carefully, tracing their trajectories backward and searching for patterns that might indicate unconventional formation mechanisms. Each new magnetar discovered is subjected to this analysis, checking whether its motion and environment are consistent with birth in a traditional supernova or whether something more exotic might be required. This work represents the cutting edge of high-energy astrophysics, the branch of astronomy concerned with the most energetic and extreme phenomena in the universe. Magnetars sit at the intersection of multiple fundamental areas of physics: the behavior of matter at nuclear densities, the generation and effects of ultra-strong magnetic fields, the mechanisms of stellar explosions, and the endpoints of stellar evolution. Understanding how they form, how many exist, and what variety of formation channels might produce them is considered one of the key questions in the field. Every magnetar is a natural laboratory testing physics in conditions we can never reproduce on Earth, where magnetic fields, densities, and temperatures exceed anything achievable in our laboratories. The theoretical models that describe magnetar formation and evolution involve some of the most complex physics in astrophysics. Researchers must account for general relativity, which becomes important when gravity is strong enough to warp spacetime significantly. They must model nuclear matter, understanding how protons and neutrons behave when compressed to densities exceeding those in atomic nuclei. They need to track magnetic field evolution in highly conducting fluids under extreme conditions. They must simulate supernova explosions and stellar collapses in 3 dimensions, following the complex hydrodynamics of shock waves and convective flows. Even with modern supercomputers, capturing all these processes accurately in a single simulation remains at the edge of computational capability. Each unusual magnetar observation provides crucial data to test and refine these complex models. When theory predicts that all magnetars should have nearby supernova remnants, and we find one that doesn't, it tells us our models are incomplete. When we discover magnetars in unexpected locations or with unexpected properties, we learn that our understanding of stellar death still has gaps. Science advances through this dialectic between theory and observation, with observations revealing phenomena that theory must then explain, and theory making predictions that observers can test. The zombie star, in its mysterious journey through the galaxy, exemplifies this process. A single object whose properties challenge our current understanding and demand new explanations. The question of whether other magnetars might have formed through white dwarf collapse connects to larger questions about the diversity of neutron star formation mechanisms. For decades, astronomers recognized 2 main pathways to creating neutron stars: core collapse supernovae of massive single stars, and electron capture supernovae in intermediate mass stars, a variant where the collapse is triggered by electrons being captured by nuclei rather than iron core formation. The white dwarf collapse channel would represent a third mechanism, expanding the picture of how these objects can form. There may be other mechanisms we haven't yet recognized, other pathways to creating neutron stars that operate under special circumstances or in specific environments. Understanding the full variety of formation mechanisms matters for modeling galactic evolution and the chemical enrichment of the universe. Different types of stellar explosions and collapses eject different amounts and types of elements into space. Core collapse supernovae are the primary sources of elements like oxygen, silicon, and iron in the universe, produced in the massive star's interior and scattered by the explosion. Type Ia supernovae of white dwarfs contribute different element ratios and are particularly important sources of iron group elements. If white dwarf collapse can produce neutron stars without exploding, this represents a different pathway that locks material away in the neutron star, rather than enriching the interstellar medium. The relative rates of these different processes affect the chemical composition of subsequent generations of stars and planets. The study of magnetar formation rates and mechanisms also connects to gravitational wave astronomy, one of the newest and most exciting frontiers in observational science. When 2 neutron stars orbit each other, they gradually lose energy to gravitational wave radiation, slowly spiraling inward until they eventually merge in a catastrophic collision. These neutron star mergers produce gravitational waves detectable by instruments like LIGO and Virgo, and they're also believed to be the primary sites where the heaviest elements in the periodic table, like gold and platinum, are synthesized. To predict how often these mergers occur and what signatures they should produce, astronomers need accurate models of the neutron star population, including how many exist, how they formed, and how their properties are distributed. Additional formation channels that contribute to the neutron star population affect these predictions. As we contemplate the zombie stars racing through space, we're forced to confront the sheer violence and energy scales of the universe. The event that launched this magnetar, whether a supernova explosion or a white dwarf collapse, released energy equivalent to the entire energy output of our Sun over its 10 billion year lifetime, released in seconds. The magnetic field it harbors contains energy that could rearrange matter at the atomic level across hundreds of miles. The object itself is so dense that a fragment the size of a sugar cube would weigh as much as all of humanity combined. These are the kinds of extreme conditions that test the fundamental laws of physics, pushing matter, energy, and fields to their absolute limits. Yet for all its extremity, the zombie star is not unique in kind. Throughout our galaxy and across the universe, magnetars are being born, are bursting with energy, are cooling and fading. Neutron stars by the millions populate the Milky Way, invisible remnants of stars that died before humans existed, before Earth formed, before the sun ignited. Each has its own history, its own unique journey from birth in stellar collapse to its current state. Some are in binary systems, locked in orbital dances with companion stars. Some are isolated wanderers like the zombie star, cast out from their birthplaces by asymmetric explosions. Some are young and energetic, others ancient and cold. Together they form a vast, mostly invisible population, the accumulated stellar corpses of billions of years of galactic history. The detective work required to uncover the zombie star's origin story exemplifies how modern astronomy operates. Gone are the days when individual astronomers worked alone with single telescopes, making discoveries through patient observation. Today's astronomy is a collaborative, technological enterprise involving hundreds of researchers, multiple observatories operating across the electromagnetic spectrum, from radio waves to gamma rays, sophisticated data analysis pipelines, and complex theoretical models. Understanding a single object like SGR 0501 plus 4516 requires combining observations from Hubble, Gaia, X-ray satellites, radio telescopes, and ground-based optical instruments, each contributing different pieces of information. It requires comparing the observations to detailed simulations of supernova explosions and stellar collapses run on supercomputers. It involves tracing trajectories backward through the galaxy's gravitational field, searching databases for potential birth sites, and eliminating possibilities one by one. This collaborative, multifaceted approach reflects the complexity of the universe itself. No single observation or measurement tells the complete story. Objects and phenomena reveal themselves through multiple lines of evidence, viewed from different angles with different instruments, sensitive to different properties. The zombie star's nature as a magnetar was established by X-ray observations of its bursts and spectrum. Its tremendous velocity was measured through precise positional astronomy, using optical and infrared telescopes. Its trajectory was reconstructed by combining these velocity measurements with models of galactic gravitational potential. The search for its origin involved surveying supernova remnants, star clusters, and binary systems in the relevant region of the galaxy. Only by integrating all these different types of information could researchers recognize the mystery and begin proposing solutions. The story of the zombie star also reminds us how much we still don't know about the universe, even relatively nearby in our own galaxy. This object is only 15,000 light-years away, close enough that light from its formation would have reached Earth around the same time humans were creating the first permanent settlements. Yet we didn't know it existed until 2008, and more than 15 years later, we still cannot definitively explain where it came from. If such mysteries persist for objects in our galactic neighborhood, imagine what unknowns lurk in the vast spaces between galaxies, in the distant reaches of the observable universe, or in the epochs of cosmic history we can observe only dimly through ancient light. Each generation of astronomers believes it understands the universe somewhat better than the last, and this is certainly true in terms of accumulated knowledge and theoretical sophistication. We know the universe is expanding and accelerating. We understand stellar evolution from birth to death. We've detected gravitational waves, imaged black hole shadows, and found thousands of planets orbiting other stars. Yet the universe consistently reminds us of our ignorance, presenting phenomena we didn't predict, objects that don't fit our models, and mysteries that resist easy solution. The zombie star is one such reminder, a stellar corpse that refuses to follow the script we'd written for it. Perhaps the most profound aspect of studying objects like this magnetar is what it reveals about the nature of scientific inquiry itself. Science is not primarily about having answers, but about asking better questions and pursuing those questions wherever they lead. When the trajectory analysis showed that the zombie star couldn't have come from HB9, researchers didn't abandon the investigation or force the data to fit their preferred theory. They acknowledged the discrepancy and began searching for alternative explanations. When no conventional formation site could be found, they didn't declare the problem unsolvable, but instead considered more. Exotic possibilities, stretching the boundaries of accepted theory to accommodate the observations. This willingness to follow evidence even when it leads to uncomfortable or inconvenient conclusions. This commitment to saying, "I don't know," when knowledge is genuinely lacking, represents science at its best. The white dwarf collapse hypothesis itself emerged not from observation, but from theoretical predictions that such a process should be possible under certain conditions. For years, this remained a largely academic possibility, an interesting theoretical footnote with little observational evidence to support or refute it. The zombie star may represent the first concrete example of this process in action, transforming a theoretical curiosity into an observed phenomenon. This progression from theory to observation happens repeatedly in astrophysics. Black holes were predicted by general relativity decades before any observational evidence for them existed. Gravitational waves were anticipated for a century before their direct detection in 2015. Neutron stars themselves were proposed theoretically in the 1930s, but not observed until pulsars were discovered in 1967. Theory and observation advance together, each informing and constraining the other, gradually building a more complete and accurate picture of reality. The implications of the white dwarf collapse mechanism extend beyond just explaining one mysterious magnetar. If confirmed, this discovery would affect how we understand the population of compact objects in the universe, the term astronomers use for neutron stars, black holes, and white dwarfs, the dense remnants left behind when stars die. Current surveys and catalogues of these objects are based partly on assumptions about how they form and how common different formation channels are. If white dwarf collapse contributes significantly to the neutron star population, particularly to magnetars, then population synthesis models that predict how many of these objects should exist need to be revised. This could affect estimates of event rates for gravitational wave detections, predictions for supernova rates in different types of galaxies, and our understanding of how matter cycles through galaxies over cosmic time. The possibility also raises intriguing questions about what happens in the moments of white dwarf collapse. Does the transformation from white dwarf to neutron star happen smoothly, or does it involve violent instabilities? Is there any electromagnetic signal we might detect if we happen to be observing at the right moment? Traditional core collapse supernovae announce themselves spectacularly with brilliant optical displays lasting weeks or months as radioactive decay powers the expanding debris. A collapsing white dwarf might produce a much more subtle signature, perhaps a brief burst of X-rays or gamma rays, or a pulse of neutrinos carrying away the binding energy released as matter compresses to nuclear densities. Such signals would be far more difficult to detect than supernovae, which may explain why we've never definitively observed a white dwarf collapsing in real time, despite the fact that, if this mechanism operates, it should happen occasionally in our galaxy. The detection challenge highlights an important reality of modern astronomy. We are often searching for signals we can barely detect or phenomena that occur rarely and unpredictably. The universe does not arrange itself for our observational convenience. Most of space is empty. Most of time is uneventful. The extraordinary events that shape cosmic evolution, the supernova, explosions, the black hole mergers, the formation of new stars, happen sporadically and at random locations. Even with our growing fleet of telescopes and satellites constantly monitoring the sky, we catch only a tiny fraction of these events. We survey a small patch of sky and miss something extraordinary happening just outside the field of view. We observe at optical wavelengths and miss a transient that shines primarily in X-rays. We look for a few hours and miss something that flared and faded in minutes. The zombie star itself announced its presence with bursts in 2008, but it may have been racing through space for thousands of years before that, invisible and unnoticed. This observational challenge makes the discoveries we do make all the more precious. Each detected magnetar, each unusual trajectory, each mysterious object represents a rare glimpse into processes that usually occur unseen. The sample of 30 or so confirmed magnetars in our galaxy may represent only a small fraction of the total magnetar population. Many may be too faint, too distant, or oriented unfavorably for detection. Others may have never undergone the kind of dramatic outburst that brought the zombie star to our attention. Statistical analyses of incomplete samples are always tricky, requiring careful accounting for selection effects and detection biases. Nevertheless, from this limited sample, astronomers work to infer the properties of the full population, using techniques similar to how biologists might study an ecosystem by sampling a small area and extrapolating to the whole, or how pollsters infer voting patterns from surveying a subset of the electorate. The study of the zombie star and objects like it also illustrates the importance of patience in astronomical research. Major discoveries rarely happen overnight. The magnetar was first detected in 2008, but the realization that its trajectory didn't match any plausible origin point came years later, after sufficient time had passed for precise, proper motion measurements. The accumulation of data from multiple instruments, the refinement of analytical techniques, the development of new theoretical models, all of this takes time. Individual researchers may spend entire careers studying small aspects of these complex problems, gradually accumulating the expertise and data needed to make meaningful progress. Young scientists who began studying this magnetar as graduate students in 2008 are now established researchers in mid-career, and the mystery of its origin remains unsolved. Yet this slow, patient accumulation of knowledge is how science works. We do not expect instant answers to complex questions. We build on previous work, generation after generation, each contribution adding to a growing edifice of understanding. The researchers studying the zombie star today benefit from decades of previous work on neutron stars, magnetars, supernova remnants, and stellar evolution. They use analytical techniques developed by earlier generations, instruments designed and built by teams of engineers and scientists, and theoretical frameworks constructed through countless papers and conferences. In turn, their work will provide the foundation for future researchers who will have better instruments, more complete data, and new insights that come only with the perspective of time. Looking forward, the next generation of astronomical instruments promises to shed new light on mysteries like the zombie star's origin. the Square Kilometre Array, a next-generation radio. Telescope currently under construction will survey the sky with unprecedented sensitivity and resolution, potentially detecting faint supernova remnants or other structures that previous instruments missed. The extremely large telescope and other ground-based optical telescopes, with mirrors 30 meters or more in diameter, will observe fainter objects and resolve finer details than current instruments can manage. Space-based X-ray observatories with greater sensitivity will catch brief transient events and study magnetars in more detail. Each advance in instrumental capability opens new windows on the universe, revealing phenomena that were previously invisible or undetectable. The computational tools available to astronomers are also advancing rapidly. Modern simulations of supernova explosions and stellar collapses can track the evolution of matter, magnetic fields, and radiation in 3 dimensions with increasing fidelity, though still not capturing every relevant physical process. Machine learning algorithms are being applied to astronomical data in new ways, finding patterns and anomalies that might escape human attention. Vast databases of astronomical observations containing information on billions of objects can now be queried and cross-referenced in ways that would have been impossible a generation ago. These computational advances complement the instrumental advances, helping astronomers extract maximum information from the data they collect and test theoretical models against observations with increasing rigor. The mystery of the zombie star also resonates with deeper questions about cosmic violence and the energetic processes that shape the universe. We live in what seems to be a relatively calm cosmic environment, on a stable planet, orbiting a well-behaved star in a quiet region of the galaxy. Yet this tranquility is an illusion, or at least represents an incomplete picture. The universe is full of violence operating on scales we can barely comprehend. Stars explode with the energy of billions of nuclear weapons. Black holes collide and merge, shaking the very fabric of space-time. Massive stars are born and die in cosmic eye blinks compared to the billion-year timescales of galaxies. The zombie star racing through space at 100,000 miles per hour, carrying a magnetic field that could disintegrate matter at atomic distances, exemplifies this hidden violence. This violence, paradoxically, is creative as well as destructive. The supernova explosion, or white dwarf collapse, that created the zombie star also produced and scattered elements essential for life. The iron in our blood, the calcium in our bones, the oxygen we breathe, all were forged in stellar furnaces and distributed through space by stellar explosions. The magnetar's intense magnetic field and energetic bursts may contribute to heating the interstellar medium, affecting how and where new stars form. Even black holes, often portrayed as cosmic destroyers, play essential roles in regulating star formation in galaxies through their jets and outflows. The universe's creative and destructive aspects are inseparable, 2 sides of the same processes operating across cosmic time. Understanding objects like the zombie star helps us place ourselves in this cosmic context. We are made of star stuff, as Carl Sagan famously noted, our atoms forged in stellar furnaces and scattered by stellar deaths. The galaxy we inhabit has been shaped by billions of years of star formation and stellar evolution, each generation of stars enriching the interstellar medium with heavier elements, gradually transforming the primordial hydrogen and helium from the Big Bang into the complex mixture of elements we find today. Every neutron star, including our zombie star, represents not just a dead star, but a repository of processed matter, elements created through nuclear fusion and neutron capture, locked away in a compact remnant rather than returned to space. Over time, these neutron stars may merge with companions or be disrupted by close encounters, eventually returning their material to the galactic ecosystem, but on timescales of billions of years. The study of objects at the extremes of physics, like magnetars, also advances our understanding of fundamental laws of nature. The conditions inside a neutron star exceed anything we can create in laboratories on Earth. The density approaches that of atomic nuclei. The magnetic fields are millions of times stronger than anything we can generate artificially. The matter exists in states that we can describe theoretically but never directly examine. Observations of neutron stars provide our only window into how matter and fields behave under these extreme conditions. Every precise measurement of a neutron star's mass, radius, spin, or magnetic field strength constrains theoretical models of nuclear matter and tests our understanding of how matter behaves at densities where the distinction between individual protons and neutrons begins to break down. The zombie star's magnetic field, in particular, tests our understanding of magnetism in extreme conditions. Quantum electrodynamics, the theory describing how light and matter interact, predicts unusual effects in ultra-strong magnetic fields. Above a critical field strength called the Schwinger limit, about 10 to the 13th Gauss, the vacuum itself can become unstable, with the magnetic field strong enough to create particle-antiparticle pairs from empty space. The zombie star's magnetic field, at 10 to the 15th Gauss, exceeds this critical value by a factor of 100, placing it firmly in the regime where these quantum effects should be important. Observations of how such magnetars emit radiation and how their magnetic fields evolve over time provide tests of quantum electrodynamics in conditions that can never be reproduced in terrestrial laboratories. These connections between astrophysical observations and fundamental physics illustrate the unity of physical law across the universe. The same laws that govern atoms in a laboratory apply to matter in neutron stars, in the cores of stars, in the jets from black holes, and in the aftermath of the Big Bang. Physics is not a collection of separate theories applying to different contexts, but a unified framework describing how matter, energy, space, and time behave under all conditions. When we observe magnetars and find they behave as theory predicts, or when we find discrepancies that force us to refine our theories, we are testing and improving our understanding of these fundamental laws. The universe becomes a vast laboratory, providing experiments and conditions we could never create artificially, challenging us to extend our theories into new regimes and verify that they work universally. The philosophical implications of discovering that we still cannot explain where a relatively nearby stellar corpse came from are worth contemplating. Humanity has made extraordinary progress in understanding the universe. 500 years ago, we thought Earth was the center of creation with the sun and planets revolving around it. 200 years ago, we didn't know our sun was just one star among countless billions. 100 years ago, we didn't know other galaxies existed beyond the Milky Way. 50 years ago, we'd never detected a planet orbiting another star or observed gravitational waves. The pace of discovery and the expansion of our cosmic horizons have been breathtaking. Yet mysteries persist even in our own galactic neighborhood, reminding us how much remains unknown. This should inspire humility about the limits of current knowledge without descending into skepticism about the scientific enterprise. Science is humanity's most powerful tool for understanding reality precisely because it embraces uncertainty and insists on evidence. Scientists studying the zombie star freely admit they don't know where it came from. They publish this uncertainty, describe the failed attempts to match it with known supernova remnants and propose alternative hypotheses that future observations might test. This honest accounting of what we know and don't know stands in stark contrast to dogmatic claims to absolute knowledge. The willingness to say we don't know is a strength, not a weakness, because it motivates continued investigation and prevents premature closure on incomplete explanations. As future observations hopefully resolve the mystery of the zombie star's origin, whether confirming the white dwarf collapse hypothesis or revealing some entirely unexpected mechanism, the knowledge gained will immediately raise new questions. If white dwarf collapse does produce magnetars, how common is this process? What fraction of the magnetar population formed this way rather than in traditional supernovae? Do white dwarf-formed magnetars differ systematically from supernova-formed ones in their properties? If magnetars are indeed responsible for some fast radio bursts, can we distinguish bursts from white dwarf-formed magnetars versus supernova-formed ones? Each answer opens new avenues of inquiry, new puzzles to solve, new phenomena to explain. This endless frontier of knowledge characterizes astronomy and science more broadly. We never reach a point where everything is understood and no questions remain. Each discovery illuminates some aspect of reality while simultaneously revealing new mysteries lurking in the shadows. The more we learn, the more we realize how much remains to be learned. The expansion of knowledge is not a linear progression toward some final theory of everything, but an exploration of an effectively infinite landscape of phenomena, operating across scales from quantum foam to cosmic horizons, from the first microseconds after the Big Bang to the deep future of a universe expanding and cooling toward heat, death trillions of years hence. For the zombie star itself, racing through the galaxy at its tremendous speed, the concerns of human astronomers are irrelevant. It does not care that we wonder about its origins or that we cannot match its trajectory to any known supernova remnant. It follows the path dictated by its velocity and the galaxy's gravitational field, slowly cooling and fading as the eons pass. Its intense magnetic field will gradually weaken over millions of years as electrical currents in its interior decay and the field bleeds energy into space. Its violent outbursts will become less frequent and eventually cease as the stellar corpse settles into quiescence. In 1 billion years, it will have completed several orbits around the galactic center, passing through spiral arms and regions of active star formation, an invisible wanderer moving through an ever-changing galactic landscape. From our limited human perspective, watching from our small, rocky world in this particular moment of cosmic history, the zombie star represents a puzzle, a challenge, and an opportunity. The puzzle is where it came from and what mechanism launched it on its extraordinary journey. The challenge is developing the observational and theoretical tools to solve that puzzle definitively. The opportunity is what we learn in the process, not just about this one object, but about stellar death, neutron star formation, white dwarf evolution, magnetic field generation, and the myriad other topics that intersect in this single case. Every mystery we work to solve teaches us not just about the specific phenomenon at hand, but about how to approach unknowns, how to test hypotheses, how to extract understanding from incomplete information. The story of SGR 0501 plus 4516 reminds us why we study the universe, why we build telescopes and satellites, why we dedicate careers to puzzling over faint smudges of light captured by detectors and transformed into data. We do this because the universe is endlessly fascinating, because each answered question reveals new mysteries. because understanding our cosmic context helps us understand ourselves and our place in the grand scheme. We do it because we can, because humans, uniquely among Earth's creatures, have the curiosity to ask how and why, the intelligence to develop methods for answering those questions, and the persistence to pursue understanding across generations. The zombie star, in its lonely journey through the galaxy, connects us to the vast cosmos beyond our planet, reminding us that we are part of something far larger than ourselves. As we conclude this exploration of one mysterious magnetar racing through our galaxy, we return to the fundamental questions with which we began, now enriched by understanding what makes those questions so difficult to answer. Where did the zombie star come from? We have proposed the white dwarf collapse mechanism as a leading candidate, but definitive evidence remains elusive. Why is it moving so fast? The asymmetric nature of stellar collapse and explosion can impart tremendous velocities to the resulting neutron star, but the specific dynamics that launch this particular object remain unknown. What does this tell us about the violent deaths of stars? It suggests that stellar death is more diverse and complex than our models have captured, that multiple pathways exist for creating the exotic objects we observe, and that the universe still holds surprises even in phenomena we thought we understood well. The zombie star continues its journey through the galaxy, a stellar corpse that refuses to follow our neat theoretical predictions, a reminder of cosmic violence operating on scales beyond human experience, a mystery that challenges our understanding and invites continued investigation. It embodies the frontier between knowledge and ignorance, between the settled science of stellar evolution and the cutting edge of research into extreme physics. In this single wandering object, we glimpse the broader truths about scientific inquiry: that nature is under no obligation to make sense to us, that understanding comes through patience and persistence, and that the universe consistently proves more strange and wonderful than we imagine. The story of this magnetar racing through space at impossible speeds with no clear home is not yet complete. The final chapter remains to be written, waiting for future observations, new instruments, and perhaps insights we cannot yet anticipate. Until then, the zombie star races on through the darkness, carrying its secrets with it, a cosmic riddle hurtling through the galaxy at 100,000 miles per hour, leaving us to wonder and to search for answers among the stars. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.